Aloha and welcome to the second lecture for the scientific method. This is Social Science 300. My name is Kanoa Meriwether. The reading for this lecture is still Induction, Deduction, the Scientific Method by Irving Rothschild. You're also going to want to read David Hume and Karl Popper and the 100 Essential Thinkers by Philip Stokes. And again, you've got your option of reading Induction, Deduction, the article from the Internet Encyclopedia of Philosophy, and the scientific paper is a fraud by Peter Medawar. Pardon me. Those are, again, optional articles. The material in those articles is not going to be part of the exam, but it will help you to understand maybe the perspectives and the things that are being discussed in the other articles. So we've been talking about deductive reasoning as a form of logic and a scientific process. We've also got this other form, which is called inductive reasoning. And the distinction between deductive reasoning and inductive reasoning that is the most important for you to remember is that deductive reasoning will give you a 100% guaranteed true conclusion if you do it right and you start with a true premise. Inductive reasoning cannot guarantee the truth of the conclusion the way that deductive reasoning does. Yeah? So that's the basic key distinction between deductive and inductive. Deductive, if done right, gives you a 100% guaranteed true conclusion. Inductive reasoning, no matter how well you do it, is not as logically powerful and cannot give you a 100% guaranteed true conclusion. Yeah? We've also talked about the direction of deductive reasoning, specifically that it goes from a very general statement that is assumed to be true and goes to more specific statements based on that general understanding. With inductive reasoning, it tends to move in the other direction, where we go from very specific statements, specific observations of nature, to more general underlying principles or the process that explains them. So, for example, inductive reasoning is illustrated by the story of Newton coming up with the theory of gravity. He's sitting on a hilltop underneath an apple tree, and an apple falls off of the apple tree, and in the story it hits him on the head. But basically he just observes an apple falling from an apple tree and starts thinking about, why do apples fall from trees instead of remain suspended there or float into space? And this is a process that occurs the same, as far as I know, everywhere around the planet. So Newton goes from these very basic observations, very specific observations of nature, and says there is some general process or principle that underlies this observation, these patterns, yeah? And this process or this principle is something that I can explain. I can study, I can observe, and I can get a better understanding of it. And that's where he comes up with, his understanding of this process, and he calls it gravity. And says that gravity works in certain ways, and so on and so forth. So that's inductive reasoning. If you can strengthen your argument or your hypothesis by adding another piece of information, you're probably using inductive reasoning. Yeah? Because what you're doing with inductive reasoning is you're adding specific observations to the pile of knowledge. Yeah, is this also true? Is this also true? Is this also true? So inductive reasoning is much more open-ended and exploratory than deductive. Deductive has to stick to that original premise. You have to follow that form correctly. Otherwise, you're not doing it right. You will not have a guaranteed true conclusion. But with inductive reasoning, you don't have to stick to the original premise. It's open-ended and exploratory. You're trying to come up with a premise that explains all these observations. So because it's much more flexible and it starts without truth, it's much more prone to misuse than deductive reasoning. Here's another example of inductive reasoning. Charles Darwin became curious about the observations he was making, individual observations about the natural world. He's seeing patterns, things like he goes to mountaintops in these remote areas and he finds fossils of marine life. He finds fossils that tell him that at one time this mountaintop must have been underwater. Yeah. He also finds fossils and remains of plant and animal life of varying similarities that appear to be extremely similar except for one small difference, right? So over the years, he collects all of these observations, all of these individual observations about the natural world, about patterns he sees in the natural world. And this leads him to come to a hypothesis about the pattern that, or about the principles that are underlying these observations. Why does he see, this varying similarity among plant and animal life? Well, maybe it's because there's some sort of process that explains what creatures live and what creatures die. Yeah, and this brought him to his theory of natural selection, his theory of what's known as fitness, and what we call the theory of evolution. But we can't just run to Darwin yet. We need to talk about the empiricists, and one of the strongest empiricists of his time and in all time, I guess, is David Hume. David Hume is one of the leaders of the group that was known as the British empiricists. Yeah, and they stood in opposition to the continental rationalists, and they said, it's wrong to try and identify new information using thought alone. We must use our senses. We must be able to observe and quantify the world and use that data to better our understanding. But he also recognized that we can't just take things on face value. We have to be skeptical. We have to be critical of what we're seeing and to ask ourselves, is it really, is that really what we're seeing, or is that our interpretation of what we're seeing? He also helped to criticize the inductive method, and his criticism remains current today. So remember, the inductive method is formulating laws based on our observations of reoccurring phenomenal patterns in the world, right? We say, oh, look, it seems like, the water isn't as high in the ocean today. You go down to the pier and you notice that the boats are sitting lower than they normally do. And then you observe that, later on in the day, the boats are sitting up higher. And you notice that this happens, roughly about, at least twice a day. And, if you spend 24 hours looking at it, you'll notice that it happens 4 times a day. So you come up with some basic law that says this is what's going on with the water and why it rises and goes down. That's the inductive method. Well, Hume said that that we've got a problem with induction. Although it's natural and we tend to use it as a matter of course, there's nothing logically decisive about induction. Yeah, and to show us that, he gives us the argument of whether or not the sun will rise tomorrow. Yeah, most of us think that the past acts as a reliable guide to the future because in our lifetimes it does. Right, the way things worked yesterday are typically going to be the way things work today. Not always, not for sure, but so much so that we count on it without even asking ourselves if today is going to be the same as yesterday. So we believe that all the patterns in the behavior of objects in the past will persist in the future. Our watch told time yesterday, it will tell time today. Yeah, our TV showed us TV shows and whatever yesterday, it will do the same today. We believe that the patterns of things that we've observed in our lifetimes will continue. They will persist into the future. But there's no logical necessity for that. Yeah. So this belief in the persistence of regularities is sometimes called the principle of the uniformity of nature. Yeah. The idea that the sun has always risen as far back as any scientist can identify. As long as the Earth has existed, the sun has risen because this is the process of orbit, of the Earth around the sun. But how does that then guarantee that it's going to happen tomorrow? So we're saying basically that we can't justify that the sun will rise tomorrow because it did yesterday. That's not a logical justification. Just because it rose yesterday doesn't mean that something's going to happen between now and tomorrow that won't stop it. Yeah, the sun could explode. Our planet could fly off of its axis and fly into, out of the solar system. We cannot logically justify our belief that everything that is the way it is today will be the same way tomorrow. And Hume did his best first to find some way to justify that belief. Yeah, he found two justifications that most folks fall upon, and wound up rejecting them both. Yeah, first justification: tomorrow must resemble today. As a matter of logical necessity, the future must resemble the past. But Hume says that is not true. That uniformity principle cannot be demonstrated. Just because you're alive today doesn't mean you won't be dead tomorrow. Yeah? Just because your dog follows your commands today doesn't mean it will follow your commands tomorrow. It could get rabies and it could attack you. Yeah? There's always a possibility that things could be different tomorrow than they are today. So nothing makes the principle of induction logically necessary. Nothing makes this notion that because things are the way they are now, they will always be. The second justification that Hume examined is that appeal to the past reliability. Yeah, and that's basically saying because it's always worked before, it will probably continue to work. Yeah, and Hume says basically this is just a fallacy of circular reasoning. Circular reasoning is a common fallacy that people make. Here's an example. Only an untrustworthy person would run for office. The fact that politicians are untrustworthy is proof of this. This argument is circular reasoning basically because it relies upon its own proposition that politicians are untrustworthy in order to support its central premise. Yeah, it's saying basically it's assuming that its central point is already proven, and it uses this in support of its central point. Another example would be opium induces sleep because it has a soporific quality. Yeah, that's saying basically opium makes us sleep because it has a sleep-inducing quality. Yeah, that's circular reasoning. Same thing goes with that second justification. He's saying we should not fall prey to the fallacy that because it was the same yesterday, it should be the same tomorrow. Yeah. However, he says, we use induction as our everyday reasoning. We do not ask ourselves, deductive questions about our environment. We instead ask ourselves inductive questions. Our daily behavior depends on patterns of repeated experience, right? So you're driving to work. You can do it almost, for a lot of folks, they can do it almost automatically without even having to ask themselves, what road do I need to take now? Yeah, and how much further do I need to go before I see my turn off or one thing or another? It becomes a pattern of repeated experience that we no longer question. We just do. Yeah. But that is based on induction. Yeah, that is based on induction by enumeration. Every time I've driven to work, I've taken this road to that highway, taken this exit, driven, to this driveway, parked my car, and walked into work. That does not mean then that it's always going to be the same place. You might get another job someplace else, and your drive to work would be different. Hume argued. He says, every day we will wake up and we will make ourselves a sandwich or make toast or something because we believe that bread is food that will nourish us, and it has in the past. But what if overnight someone snuck in and poisoned your bread? Yeah, it's conceivable that the bread that you're making toast with could poison you, but you don't ask yourself that question. You just rely on your inductive reasoning that it never has poisoned you in the past, so you're just going to go for it. Yeah. if you insisted on sound deductive justifications for everything rather than inductive, you'd probably starve to death, as I would. Yeah, because we'd ask ourselves, how can I prove that this food will nourish me? And we'd have such a hard time proving it that we'd be, starving. So instead of unproductive radical skepticism about everything, Hume advocated, that we use our practical skepticism based on common sense. And that means that we have to accept the inevitability of induction. We're going to use induction in our everyday reasoning. It's inevitable. But that doesn't mean that we should just accept it and say that we can just turn our back and say everything will always be the way that it has been. Yeah. So we accept that induction is inevitable because we need to get to work, we need to feed ourselves, but that doesn't mean that we should only rely on induction. Pardon me. So as I said, science uses both deductive and inductive methods, yeah? Both deductive and inductive logic. With inductive logic, we're talking about observing specific cases, making specific observations, and generalizing those results to a larger population or a larger scope. So another example, Galileo constructed these wooden ramps, and he rolled balls down these wooden ramps to identify some of the basic principles of motion and that sort of thing. And he wrote about these balls rolling and how basically they would roll in a certain way and gain momentum or lose momentum in certain ways. And so we would assume, based on induction by enumeration, that we can that because those balls continue to show the same principles, and that we can construct this a ramp the same way that Galileo did and have balls the same size and mass that Galileo had and roll those down, do the exact same experiments. Yeah. So we would use induction to say, well, then these principles are the same in the natural world, and we can generalize from these balls rolling down these wooden ramps to the events of spheres and planes, in all eventualities, right? Another example is Darwin's theory of evolution, again based on his specific observations of flora and fauna, and all of these observations lead him to his generalization of this idea that what he's seeing is a pattern of natural selection, that nature selects organisms to survive based on whether or not they're a good fit for their environment. So induction works great. However, it's got a problem. The problem is that induction by enumeration will never give us enough evidence for a foolproof conclusion. No matter how much evidence we have for a conclusion, the conclusion based on induction could always be conceivably false because we can never observe every event or every instance. So when we're using induction, the best we can say is that it is unlikely that our conclusion is false, yeah? But we cannot say it is highly likely that our conclusion is true. So when we have theories that are based on induction, evolution for example, it can never be proven absolutely true. So there's always a possibility for an exception to a theory when a theory is based on induction. Yeah. So that's one of the problems that we have to deal with, because scientists can't say this is 100% fact. All they can say is all of our observations support this theory. Yeah, but that doesn't mean that they aren't going to have another observation tomorrow that does not support this theory. So why does this exist? Why can't we say, hey, look, we've observed all examples of all wooden balls rolling down inclined planes, and so we can say for sure that they're always going to be the same. Well, let me give you a thought experiment. Yeah, it used to be called the barrel of apples, but because we're here in Hawaii, I'm calling it the barrel of mangoes. We can understand the problem of induction by imagining that we've got a barrel with 100 mangoes inside of it, yeah, you have a little bit of information about the mangoes, but not much. Yeah. So you go and you can't see inside the barrel, but you reach your hand in, you pull out a mango, and it's rotten. It's brown, it's icky, it's falling apart in your hand and that sort of thing. And you're grossed out, yeah? So based on this first observation, and we're doing induction, you're saying, I have an observation that a mango from that barrel is rotten. Let's say we're pessimistic, and we come up with a hypothesis. We say, well, based on this mango being rotten, I think all the mangoes in this barrel are rotten. But one mango, 1 out of 100, is pretty weak evidence. So let's reach in there and pull 4 more mangoes out. And unfortunately, now all 4 of those mangoes are rotten. Yeah, this is induction by enumeration. The more cases in favor of a hypothesis, the stronger the hypothesis is. So the more mangoes we pull out that are rotten, right, the more evidence we have that our hypothesis, all the mangoes in that barrel are rotten, is true. Yeah. So let's go ahead and pull out 45 more mangoes from that barrel. We've got 5 rotten mangoes. Our hypothesis is all the mangoes in that barrel are rotten. We pull out 45 more, yeah, and they're all rotten. So now we've got a pile of 50 rotten mangoes on our table, and we've got a barrel with 50 more mangoes in it. Would you bet your life savings that all the remaining 50 mangoes were rotten? Yeah. Would you bet, let's say, the life of your firstborn child, yeah, on whether or not the remaining 50 were rotten? I would not, because it is still possible that some, even many at the bottom of that barrel, are not rotten, right? So we've got 50 observations that tell us that the mangoes in this barrel are rotten, but we've got at least 50 more possible observations. So let's pull out 49 more mangoes, yeah, and we find that they're all rotten. Now we've got 99 rotten mangoes in a pile here. There's 1 mango left. Would you bet your life savings, would you bet the life of your firstborn child that last remaining mango is rotten? Most people probably would. I mean, we've got 99 rotten mangoes here. Yeah, I mean, it depends what you're betting. But you probably still have a lot of anxiety as that last mango is pulled from the barrel. Why would you have that anxiety? Because it's still possible that the hypothesis, all the mangoes are rotten, is false. It's still possible that 1 mango in the barrel is not rotten. Yeah? So no matter how many observations of our world we make, we can never see all the mangoes. Yeah? We can never know whether or not all the mangoes are rotten. Yeah? Here's another example. We imagine a boy named Alex who's raised in a little village in France. In his village there's a pond and there's a family of white swans. Alex grows up. He travels to other villages. He sees other families of swans, and they're all white. Yeah, the swans that he sees at his pond are white. The swans that he sees in other ponds are white. This is induction by enumeration, right? He's making observations. He's gathering evidence. He develops a theory. All swans are white. Yeah. So he travels to Germany, and he uses that theory. He says, based on my experience, based on the observations that I've made, I will see more white swans in Germany. And he goes to Germany, and what do you know? He goes to more ponds, and he sees hundreds of white swans across Germany. Yeah. So does that mean then that all swans are white? No. He's made a correct prediction from a false theory. His theory, all swans are white, is false. How do we know that? Because there are black swans. Yeah. Alex might spend his entire life without ever seeing a swan other than white. Yeah, and might, jot down these observations in 1,000 journals. Every single swan that he sees is white. But because he cannot make every observation of every single swan, he can never, therefore, state that his theory is 100% true, that all swans are white based on his observations. And that is the problem of induction. no matter how many observations we make, no matter how many times the sun rises. We can never say for sure, that the sun's going to rise again. We can never say for sure that all swans are white because we can never make all observations. So when science uses induction, our hypotheses can only be confirmed, but not logically proven to be absolutely true. The reason for that is because the problem of induction illustrates it is possible to deduce true conclusions. The fifth mango that we pull from that barrel will be rotten, from a premises that is false. All mangoes are rotten. Because we can deduce true predictions from a false theory, no matter how long a theory has been successful in making predictions, it cannot be known to be true absolutely. This blew my mind when I first learned about this because I was a strong adherent in scientific theory. I believed that, if we make millions of observations about evolution, that we need to be able to say that evolution is 100% fact. But no matter how many times we're able to make successful predictions based on a theory that we have, we can never know that that theory is true, is absolutely true. Because using induction, we can never make all the observations. So we're talking about reasoning, right? We've been talking about the form of reasoning that's called induction. When induction is used in science, we see it typically used to develop hypotheses and typically used to develop theories. Induction in science is basically the notion that we make observations about our world. We come up with educated guesses or hypotheses about what we're seeing, and then finally a general theory that explains the observations and the questions that we have about the patterns in the natural world. So induction is often used to develop hypotheses and theories, whereas we use deduction in the other way. We use deduction to test the hypotheses and theories that we have. We take these general statements, we make a more specific statement based on that theory, and then we go out and we test it. So we can talk about induction and deduction in terms of their uses in what's called the scientific cycle. Scientific study can start at either end of this cycle. It can start with induction or deduction. Using induction, we make an observation which motivates our curiosity. Look at those swans. I wonder if all swans are that color. If we can collect data, I need to go out and observe more swans. We can devise a hypothesis. I think that all swans are this color, and it explains this data because of genetics or whatever. And so I think all swans have this quality and blah blah blah. Or we can do a scientific study that goes with deduction. With deduction, we start with a general statement and we develop tests and predictions that are based on that general statement. So we start with this general theory: all swans are white. We can develop, we can run an experiment and collect data. We go out there and look at all the swans we can get our hands on. Does this data support our theory or not? No. We found black swans in this pond, and we found blue swans in that pond. So we've got to go back and revise our hypotheses. All swans are not white. All swans are, river fowl or waterfowl that have this quality and blah blah blah, but can be different colors. So we have to go back and change that basic statement. Science can go in either direction using induction or deduction. And this is what we mean by the cycle of science, right? It's kind of circular, and basically, there's no obvious beginning and ending point. It never really ends. It never really starts. I mean, it started so long ago, and it's so murky that it's just this sort of continuous cycle. The way that most philosophers of science viewed it for a long time as sort of progressing in this orderly fashion, where we have some well-tested and accepted hypotheses that are our scientific theories that we use to make new predictions and collect data and do experiments that allow us to either support the theory or revise the theory or develop new hypotheses that we then test some more and become either that become well accepted and become scientific theories, and goes on and on. that science is really this cumulative sort of process of gathering information. So you might be wondering, which is better, right? Induction or deduction? Yeah. Well, science uses both for a reason. Yeah. The quotes here are from Rothschild's article. Both induction and deduction are systems of logic. They're both methods of solving problems. Yeah. So it doesn't matter really. You're not really saying that one's necessarily better than the other, because they both have their flaws. They both have their problems. Deduction gives us that truth of the conclusion, but it's so rigid and we must stick so closely to the form that it's not as applicable as induction is to most of the things in our world. So whatever problem we're tackling, we need to test it. We're trying to test the validity of whatever conclusion we come up with through either induction or deduction. And, it doesn't really matter. The point is that we're trying to use valid logic and reasoning. Yeah. So Rothschild also talks about Karl Popper, and you did, you read the little page on him in the 100 Essential Thinkers. Karl Popper was a philosopher of science and a professor at the London School of Economics, who is famous for advancing what's known as empirical falsifiability as the true criterion for distinguishing a scientific theory from non-science, from what he called pseudoscience. Yeah. And what he's saying here basically is that we've got this notion of classical science being this collection of observations that only support a theory, but can never prove that theory to be true because of the problem of induction. He says, well, we don't need to worry about that, because we can instead we can advance the value of falsificationism rather than induction. He says we can just say that a theory is true until we find a single genuine counter instance that shows the theory to be false. So Popper rejected conventional explanations. He rejected the empirical inductive method because the pseudosciences, things like astrology, are heavily empirical, right? Astrology is the notion of being born under different signs and different times of the year and that sort of thing. So you're a Virgo or Capricorn, and that means that you like you like ambiguity, or you prefer reason and structure, and so on and so forth, right? Well, for Karl Popper, he said, there are these domains out there, such as astrology, that are trying to sound like a science, and they cover themselves in this cloak of empiricism and try and look more formal and more scientific because of their use of empiricism. And he says one of the ways that these pseudosciences sort of cloak themselves in empiricism is using inductive confirmation. He says, that admirers of any pseudoscience are impressed by the apparent explanatory power of, let's say, astrology, right? These theories appear to be able to explain practically everything that happened within the fields to which they refer, yeah? And basically, what he's saying is that people would get their tarot reading or whatever, and they'd be told, now is a good time to start a new business, or now is a bad time to develop a new relationship or whatever. And what they do is they go out and they seek confirmation for that theory, sort of subconsciously. So Popper's saying that pseudoscience is a threat to science, and its use of empiricism and inductive confirmation is a black eye to science, because it's pulling science down to this pseudoscientific level. So Popper says that confirmation is meaningless. Every conceivable case could be interpreted in light of the relevant theory and could not be refuted. Yeah. So he says, instead, by exclusion, for a theory to be truly scientific, it has to be stated in a manner in which it can be refuted. Every good scientific theory is a prohibition, he said. Every good scientific theory forbids certain things to happen. For example, the theory of evolution forbids a brand new species from developing at this point in time. Yeah, there's no way that could happen. If we come upon a species that has never before been seen and has no logical connection to any other species on this planet, that would be an observation that would bring the theory of evolution down. That would be falsification. So Popper says every genuine test of a theory is really an attempt to falsify that theory or an attempt to refute it. We shouldn't test a theory and try and support it. We should test it and try and falsify it. He also talked about the problem of induction. Karl Popper says that when we look at the problem of induction, it assumes that our hypotheses are conclusions and that we infer generalizations from this evidence. Popper says, no, scientific generalizations are not conclusions. Our hypotheses are conjectures. They are hypotheses on trial that must be scrutinized. Yeah. So every scientific hypothesis is always something that we are looking at with a critical eye, and we are doing our best to show any example that we can in which this theory does not hold true. Yeah, because logically, no number of positive outcomes, no number of correct instances can confirm scientific theory. But a single genuine counter instance, he says, is logically decisive, shows that the theory from which the implication is derived is false, right? So we return to the problem of induction. Karl Popper says we've got 100 mangoes in a barrel. The proposition or the hypothesis, all are rotten. Popper says that this is a hypothesis on trial that we are trying to falsify. In classical science, this statement is one that we are trying to support. Yeah. So classic science, each rotten mango that we pull out of the barrel adds support to our hypothesis that all are rotten. For Karl Popper, he says the proposition is good until we pull out a non-rotten mango. So we can pull out 90 rotten mangoes. We pull out one good one, and that means that our theory is no longer true. Yeah. So he says one genuine counter instance is enough to refute the entire theory. So what's the criticism of this? What's wrong with this? Well, the main criticism is that what he's doing is using induction to disprove a hypothesis, right? What he's saying is we have one observation that is counter to all the other observations that we have. One instance of results that runs counter to the theory. For Popper, that one instance is assumed to be sufficient evidence to discredit it. But the theory may turn out to be more correct than incorrect. Yeah. So back to the mangoes in the barrel. Even if we pull out one good mango, yeah, that means that our hypothesis, all the mangoes in the barrel, is false. But boy, it was closer to true than not, because we've got 99 rotten mangoes and one good one. Yeah, I got 99 mangoes, but a good one ain't one. Yeah, so it means that this hypothesis was a good general conclusion, or a good basic guess. It was more true than false, but it's not 100% true. Yeah. So Rothschild, basically says that Popper's ridicule of induction is based on his premise that induction requires an observation of every instance to be true, and that is really an obvious impossibility. Rothschild's example is that what matters is that most, if not all, mangoes are rotten, or his example was whether or not crows are black. What matters is that the hypothesis that all crows are black is more true than false. And that'll do it for this lecture. As always, if you have any questions about the material, about about what I've been talking about, please feel free to email me or give me a call. And we'll see you on the next lecture. A hui ho.